All right, back now, and we're looking at the fact that for certain shapes or types of orbitals, that is the outline of the most probable area where you're likely to find electrons of certain energies within an atom. For certain types of orbitals, there will be multiple possibilities for how that shape can be oriented in 3 dimensions. And how many possibilities there are will really depend on the shape that we're talking about. So for and that's what the magnetic quantum number is about, or m sub L. This is the third quantum number that we've talked about. Remember, the primary or principal quantum number is n. That's essentially the energy level or the shell number. The secondary quantum number or the angular momentum quantum number is L, and that tells you what type or what shape of orbital you're dealing with. And this is the third quantum number, or the magnetic quantum number, or m sub L. That is m with a subscript of a little l after it. And this specifies the relative spatial orientation of the individual orbital of a given type. And so maybe you've got the orbital that's dumbbell shaped. So does the dumbbell align itself along the x-axis or the y-axis or the z-axis? Well, the magnetic quantum number, or m sub L, would tell you that. Okay, so it tells you which one of those possibilities you're actually dealing with. For S-type orbitals, or that is orbitals for which the quantum number L is equal to 0, there's only one of them in any given shell. That is any given energy level. That's because S is spherical in shape, and there's only one way that you can orient a sphere, because there are no features on the sphere. It's just a sphere. And if you turn a sphere a little bit, well, it looks exactly the same as it did before. So there's only one way to orient a sphere, and that's why there's only one orbital of the S type in any given energy level. For the P type, though, as we saw from figure 621, the shape of it allows you to orient it 3 different ways in space. And so for the p-type orbitals, or L equals 1, there are 3 of those in any given energy level that has them. But remember, only energy levels starting with n equals 2 have that type of orbital. As you may have noticed, the number of orbitals of a given type increase. Well, basically, starting with 0, they increase by odd numbers. Or sorry, they increase by odd numbers. Starting with 1, 1, 3, 5, 7. That's also 2L plus 1. So if L equals 0, 2 times 0 plus 1 is 1, and that's how many orbitals of the S type that are present in each energy level. If L equals 1, then 2 times 1 plus 1 is 3, and that's how many of that type of orbital you've got. If L equals 2, that's the D-type orbitals. We already saw that there are 5 of those in any given energy level that has them, but the only energy levels that have D-type orbitals would be n equals 3 or greater. And sure enough, 2 times L plus 1 would be 2 times 2, which is 4, plus 1, which is 5. And for the L equals 3, or F-type orbitals, as we already saw, there are 7 of those in any given shell that has them, but only shells from n equals 4 on up have them. So there are no F orbitals in n equals 1 or 2 or 3. And sure enough, 2L, that is 2 times 3 is 6, plus 1 is 7. Or you can just remember 1, 3, 5, 7. Okay. The types of orbitals where there's more than one example of that type of orbital in each principal energy level, those orbitals will be degenerate. So like we saw in figure 621, px, py, and pz, they are degenerate, meaning simply that the energies of the electrons in those 3 orientations are the same as each other. Okay, so in essence, if you've got like 1 electron in the p orbitals in a given energy level, it doesn't really matter which one which one it's in, which one the electron is in, because they're all the same energy. And they're all the same energy because really the X and Y and Z axes are arbitrary. We draw them in space. It's sort of like, well, it's sort of like north and south on the globe are arbitrary. You could you could switch those around if you wanted to. Well, it's in space, in just within an atom in space, the X and Y and Z axes are even more arbitrary, because at least on Earth you have an actual axis of rotation. In an atom, you don't even have that. You got rotation going on in all different directions. So you could call something the x-axis. Somebody else might call it the y-axis, and that's just as correct. So there's no reason why the p orbitals are in any given energy level. There's no reason why they shouldn't have the same energy. And generally speaking, it's the same with the d and the f orbitals as well. All of the f orbitals within a given energy level will have the same energy as each other. And again, that's what's known as being degenerate. Okay, so just a little review of the quantum numbers we've had so far. N is the principal quantum number. That tells you the energy or the size of the area occupied by the electrons. We've got L, which is the angular momentum quantum number. That tells you the shape or the type of the area of electron habitation, or in other words, the shape or the type of orbital that you're talking about. M sub L is the magnetic quantum number, and that tells you the orientation of the specific orbital in space, or in other words, which individual orbital of a given type are we talking about. That's what M sub L tells you. Okay, so as we said before, the N is the principal quantum number. It gives the approximate energy of the electrons at least. The exact energy can vary a bit depending on the type of orbital. All of the orbitals of a given type within a given principal energy level, though, normally have the same energy. In other words, they're degenerate. And the sort of the relationship between N and L and M sub L can be seen on this diagram. It's figure 622, actually, in the textbook on pages 309 or 319. And hopefully this is sharp enough for you to see it. But this, the original diagram in the text gives you the relative energies of the various types of orbitals in the various energy levels. So we have 1s, 2s is higher than 1s, 2p is a little bit higher than 1s though, so the 2p orbitals, but notice all three of the 2p orbitals are the same energy. And then 3s is higher than 2p, but there's only one s orbital in the third shell, just like there was only one s orbital in the second shell, and there was only one s orbital in the first shell. But then you've got 3p orbitals, and there are three of those, px, py, and pz, and they're all the same energy. And in the third shell, we have the possibility of d-type orbitals as well. There are 5 of those, and they all have the same energy. And now we come to an anomaly, which can be explained through theory. But we'll get into that a little bit later. You would expect the s orbital of the fourth energy level to be higher in energy than 3d. But in fact, it's actually not. It's a little bit lower. But then the p orbitals of the fourth principal energy level are a little bit higher. Okay. It appears to me that I may have left something a little bit out. And that is the values possible for M sub L, or the magnetic quantum number. It gives you the orientation or orbital of specific, the specific orientation or the specific orbital of a given type that we're talking about. And the possible values for M sub L would be based on L. And the values can go anywhere from negative L through 0 up to positive L. And so if L equals 0, that is an S-type orbital, then M sub L must be 0. And that's because there's only one S-type orbital in each principal energy level. If L equals 1, in other words, we're talking about p-type orbitals, M sub L could be -1, 0, or +1. And there are 3 possible values for M sub L. And that means there are 3 possible orientations for p orbitals. And each one of those orientations would have a corresponding number for M sub L. So one of these would be px, and one of them would be py, and the other would be pz. If L equals 2, in other words, we're talking about d orbitals now, then M sub L could be anywhere from -2 all the way up to +2, which would mean the possible values would be -2, -1, 0, 1, or 2. Notice that's 5 different values. And that's because there are 5 orientations for d-type orbitals, as we saw in figure 621. And finally, for L equals 3 or F-type orbitals, the possible values for M sub L would be anywhere from -3 up to +3. So that's -3, -2, -1, 0, 1, 2, or 3. And that's because there are 7 possible orientations for F-type orbitals. So each one of them would have its own value for M sub L. So each one of these would correspond to a specific F orbital of all of the F-type orbitals. Okay, so I somehow seem to have left that out of my notes. So there's that. Okay, and then what we see in this figure here is the relative energies of the orbitals relative to each other. And I've written in the quantum numbers that correspond to each of these orbitals. So for the 1s orbital, obviously, actually, I guess I haven't mentioned that yet, but the way we usually refer to an orbital is by the number of the principal energy level in which it's located, followed by the letter denoting the type of orbital or the shape of the orbital. And so for the S-type orbital in principal energy level number 1, we would call that a 1s orbital. In other words, n equals 1 and L equals 0, which corresponds to S-type orbitals. And M sub L, in this case, referring to the individual orbital, would be 0, because that's the only possible value for M sub L if L is 0. Okay, and then the S-type orbital in the principal energy level number 2 would be called a 2s orbital. In this case, n equals 2, L equals 0, again, because it's an S-type orbital. And M sub L, again, has to be 0 because that's the only possible value for M sub L if L is 0. For the 2 p orbitals, that is the p-type orbitals of the second principal energy level, n is 2 and L is now 1, because L equals 1 corresponds to p-type orbitals. You've got 3 individual p-type orbitals in the second principal energy level, and so one of them will have M sub L equals -1, one of them will have M sub L 0, and one of them will have M sub L +1, because those are the 3 values that are possible for M sub L when L equals 1. -1, 0, +1. And then we go to 3s, n equals 3, L equals 0, because it's an S-type orbital, and m sub L equals 0. For the 3p, same idea as the 2p, except now n equals 3, but L equals 1, which corresponds to p orbitals, and m sub L equals -1, 0, or +1. For the d orbitals in the third principal energy level, now n equals 3, L equals 2, because that corresponds to d-type orbitals, and m sub L could be anywhere from -2 up to +2, which means you've got 5 possibilities. So one will be -2, -1, 0, +1, +2. And then 4s and 4p, it's basically the same idea as what we've been doing. So what the 4 quantum numbers really are meant to do is to identify the location of each electron in an atom. So each individual electron in an atom will have its own unique set of quantum numbers because each electron is in a unique position within the atom. So, and as we'll see in a little while, no two electrons in a given atom can have the same total set of quantum numbers. But a little complication comes up in the fact that each individual orbital can hold up to 2 electrons. So that means this 1s orbital here, you can fit 2 electrons in there. With the quantum numbers we've had so far, we have no way of distinguishing those 2 electrons from each other if they're in the same orbital. And that's why we still have to introduce one more quantum number, and that is known as the spin quantum number. This is the 4th quantum number, m sub s. The quality of spin is what allows us to distinguish one electron from another when they're in the same orbital with each other. And spin is considered to be a quality that basically just allows 2 electrons to be in one orbital together without repelling. Electrons are negatively charged, so you wouldn't expect to be able to get them into a small space at the same time without them repelling each other, sort of like the 2 north poles of a magnet. If I take these 2 little magnets here, they're stuck tightly together because they're stuck together north pole to south pole. If I try to turn them around and get them to come together, whoa, yeah, north to north or south to south, as you can see, it jumps right on my hand. It really doesn't want to do that. Boom, there you go. And that's what you'd expect electrons to do. They're negatively charged, so they should repel each other. Quantum physicists came up with this quality known as spin, and the theory is that if they have opposite spins, then they can coexist together in the same orbital at the same time without repelling. And it has to do with the magnetic field that results when charged particles are in motion. Anytime electrically charged particles are in motion, they create a magnetic field. And so if the electrons are spinning in opposite directions, then they create essentially opposite magnetic fields and they no longer repel each other. So the way that the spins are termed would be spin up and spin down. So those would be opposite spins. They don't really spin up or spin down, but basically that's just a way of saying opposite directions. Electrons are often represented graphically as a vertical arrow with half a head on it. Basically half the head is missing. And so spin up would be the half arrow pointing up, and spin down would be a half arrow pointing down if you want to represent the electrons graphically. So if you're going to have 2 electrons in the same orbital together, they need to have opposite spins, one of these and one of these. These are also known as the alpha and beta state. We don't actually use that terminology very much, but the numerical value for the spin quantum number for spin up would be +1/2, and the numerical value for spin down would be -1/2. So there are only two possible values for m sub s, or the spin quantum number. And well, that basically just confirms the fact that there's a possibility of as many as 2 electrons in the same orbital together, but that's the limit, no more than 2. Okay, so any 2 electrons in the same orbital must have opposite spin. That is sort of the finest level detail of what's known as the Pauli exclusion principle. Actually, the Pauli exclusion principle, the big picture view of it, is that each electron within an atom has a unique set of 4 quantum numbers, n, l, m sub l, and m sub s. No 2 electrons in a given atom will have all 4 of those quantum numbers being the same. At least one of those 4 quantum numbers has to be different for any 2 electrons in the same atom. When it comes right down to the nitty-gritty, the smallest level, what it really means is that any 2 electrons in the same orbital have to have opposite spin. One will be +1/2 for m sub s, and the other will be -1/2. Okay, and that's the Pauli exclusion principle from Wolfgang Pauli. All right, so if you look at the quantum numbers for atoms, or for electrons in the same atom, at least one of those quantum numbers has to be the same. So like, for instance, if you're looking at the 2 quantum numbers, or say the 2 electrons that are in this particular d orbital, both of them will have n equals 3. Both of them will have l equals 2. Both of them will have m sub l equals -2 because they're in the same orbital, but one of them will have m sub s equals +1/2, and the other one will be -1/2. So that 4th quantum number will be different. Okay, so at least one of the quantum numbers will have to be different if you're talking about 2 different electrons in the same atom. All right. And so a summary of the allowed values for the quantum numbers. This is, I found actually when I was taking tests or quizzes, it was helpful to me to sort of reproduce this from memory to sort of check to see and make sure that I wasn't violating any of the rules. We're not actually going to have any in-class tests or quizzes this semester, so you might not have to do that, but actually still it wouldn't hurt. And I haven't seen anywhere in the book where all of this information is gathered in one place. So it can actually, this is sort of a nice, concise way of summarizing what's allowed and what isn't allowed. A version of this is in table 6.1 on page 311 or 321, but I don't think it's quite as concisely stated as this is. So possible values for n, the principal energy level, or the shell number, if you will, are just positive integers. Any positive integer, 1, 2, 3, 4, 5, 10,000, I guess, theoretically is possible. Infinity, onto infinity. Values for all of the other quantum numbers depend on the value of the last previous quantum number, though. So values for L, allowable values for L, that is, depend on what the value of n was. So L possible values start at 0 and they end at n-1. So if n is 1, then L 0 is the only possible value. If n equals 2, then 0 and 1 are possible, but 2 isn't, and so on and so on and so on. So the maximum value for L is n-1. Also over here, I wrote in the letters of the types of orbitals that correspond to the different values of L. 0, 1, 2, 3 correspond to S, P, D, and F. There are other types of orbitals that go like G, H, I, J, so on, but they are so rarely encountered that we're not going to bother with those. M sub L, the quantum number that tells you which specific orbital of a given type the electron is in, has values that can range anywhere from -L up to +L, but other values are not allowed. So if L is 0, then 0 is the only possible value for M sub L. if L is 1, then M sub L can be -1, 0, or +1. That's 3 possible values, because if L equals 1, you're talking about p orbitals, and there are 3 of them in any given energy level, and so on. And then M sub S, that actually doesn't depend on the values that come before it. M sub S can be plus or minus 1/2, but those are the only possible values. Okay, I've got some examples that we can look at, but see, we're at 25 minutes for this segment, so I think I'll cut it there and come back with C in just a moment.